As you can see, this video will deal with the binomial probability distribution. Now, we're going to use this particular session as quite an introductory session. We're not going to get embroiled in a lot of detail about the formulae or about a lot of the computations. These will be the subject matter of other videos elsewhere in the course. But in this particular case, we want to introduce the idea of binomial distributions and when and why binomial distributions may be used and for what purpose. And we can look later in other situations, in other sessions, at applications of the binomial distribution in a business context. But for the moment, we just want to go through what is meant by the binomial probability distribution. So the class will look at binomial experiments and also some associated notation. I want to introduce notation, how it's written and the way it's written, and that may seem somewhat confusing as we go through it, but again, just make notes of it. It's actually quite clear the way it's written, but it may not be in a format that with which you are familiar. The binomial experiments are very important to understand. As I said, they can crop up in a lot of situations. So let's talk about the binomial experiment. It's a statistical experiment that has the following properties. It consists of n repeated trials. So there are a number of repeated trials. It's performed more than once. It's over and over and over. And out of this process of performing it over and over, the probabilities, the associated probabilities, can be computed and outcomes can be calculated. Each trial can result in just two possible outcomes. We call one of these the success and the other is the failure. So there are just two possible outcomes to a binomial experiment: pass or fail. The probability of success is denoted by P, and it's the same for every trial. The probability remains the same. If we perform the experiment now and again in an hour's time, the probability remains the same. The trials are independent. That is, the outcome of one trial does not affect the outcome of other trials. For example, if we toss a coin and it comes down heads and we toss it again, because it came down heads this time, it doesn't mean it's going to come down tails the next time. To balance it, it could come down heads the next time. In fact, we could toss the same coin 100 times and it could come down head every time. And that's not because the coin is biased or we're doing something wrong. It just means there is a probability. On every toss of the coin, the probability is 0.5 that it will come as heads. So it could come down as heads every time we toss it 100 times or even more. So the trials are independent. The outcome of one trial does not affect the outcome of the next trial. Now consider the following statistical experiment. If we flip a coin 3 times and count the number of times the coin lands on heads. This is a binomial experiment because the experiment consists of repeated trials. We flip the coin 3 times, so it's repeated. So that's one of the requirements that's been passed. Each trial can result in just two possible outcomes, heads and tails. Therefore, the probability of success is 0.5 on each trial. Well, each trial can result in just two possible outcomes, heads and tails. It's binomial. Two possible outcomes. The trials are independent. Getting heads on one trial does not affect whether we get heads on the other trials, as I said earlier. So there's our three conditions for this particular statistical experiment. Now notation, well, this may look somewhat confusing to you. Don't get too worried about it. It's important to understand what the notation is saying and what it means. So we'll just explain the notation. And this notation is related to the binomial probability. So x is the number of successes that result from the binomial experiment. So x is the number of successes. N is the number of trials in the binomial experiment. It's the number of times the experiment is performed. If we toss a coin, it's the number of times we toss the coin. P is the probability of success on an individual trial. So we know that the probability of success in getting a head when we toss a coin is 0.5. Well, that remains the same throughout. It doesn't change to 0.2 later. It remains 0.5 right throughout the experiment. Q, the probability of failure on an individual trial. Now, Q is just equal to 1 minus P. The probability of failure is just equal to 1 minus the probability of success, because the probability of success plus the probability of failure must add up to 1. And then we have n factorial. This is a mathematical expression that we often encounter when we deal with combinations and permutations and so on. So n factorial means we just simply multiply a number by its previous number minus 1. So for example, 4 factorial would be 4 times 3 times 2 times 1. That's what we mean by n factorial. So 3 factorial would be 3 times 2 times 1. 3 factorial. So that exclamation mark means factorial. And we read it as n factorial. And what it means is just, as I said, multiplying the number by 1 less than itself and then by 1 less than that again until we get down to 1. Now, the binomial expression, which is B for binomial, bracket, well, we have the probability of successes and the number of times the experiment is conducted times the probability of success. So it's the probability that in an n trial binomial experiment results in exactly x successes. Exactly x successes. Not less, certainly not more. When the probability of success of an individual trial is p, and p is a constant. P doesn't vary from one experiment to the next. We also come across this term, which is more generally encountered when we study combinations and permutations and in mathematics. But in this case, we do come across this term. It's the number of combinations of n things taken r at a time. So it's the combinations of n things taken r at a time. N C r. A binomial random variable is the number of successes x in n repeated trials of a binomial experiment. That's what the binomial random variable is. It's the number of successes x in n repeated trials of a binomial experiment. Suppose that we flip a coin twice, 2 times. We flip a coin twice and count the number of heads, count the number of successes. The binomial random variable is the number of heads which can take on the values 0, 1 or 2. So we toss the coin twice. We might get 2 tails, a tail and a tail. We toss it again. So we have no heads. We could toss the coin twice and we get 1 head. Or we could toss the coin and we could get 2 heads. So these are the possible outcomes. We're only tossing the coin twice. So we can get 0, we can get 1, or we can get 2. And the binomial distribution is as follows. The binomial distribution has the following properties. The mean of the the distribution mu. We always use mu for mean, for the average of the population. Mu x is equal to n times p. The n is the number of times the experiment is performed, and p is the probability of success. Well, the probability of getting a head is 0.5. If we toss it twice, it would be 2 times 0.5, which is just equal to 1. So if we toss a coin twice, we'd expect to see one head. That's what we would expect. We might be surprised to get two heads. Or we might also be surprised and get two tails, no heads. But we would expect to see one. The variance, I'm not going to prove this, but the variance, which is called sigma squared x, variance is sigma squared, that's equal to n times p times the probability of getting a tail, 1 minus p. So that's the variance of x. The standard deviation is always just the square root of the variance. So standard deviation is the square root of the variance, and that's what we've got there. Now the number of heads is 0, 1 or 2. That's what we can get. We toss the coin twice. We get no heads, we get one head, we can get two heads. The probability of getting, let's say, one head, probability of getting one head is NP. So we'd expect NP, so we expect one head, which is 0.5. The probability is 0.5. No heads, 0.25. Two heads, 0.25. So we'd expect that sort of table to emerge. That would be our expectation. Now, binomial formula and binomial probability. Well, binomial probability refers to the probability that a binomial experiment results in exactly x successes. Exactly x successes. For example, in the table we had earlier on the previous slide, we see that the binomial probability of getting exactly one head in two flips of a coin is 0.5. So that's the probability. Now, given the probability of getting a certain outcome x in n trials with the probability p of getting this outcome x, we can compute the binomial probability based on the binomial formula. Now, the binomial formula, suppose that a binomial experiment consists of n trials and results in x successes. If the probability of success on an individual trial is p, then the binomial probability is. And I appreciate that looks quite difficult. If you haven't done any statistics before, that will look quite difficult. But all it's saying is that the binomial probability of getting x in n trials with a probability of p is equal to the combination of n, x, is the way we have x outcomes, the number of ways we can have x outcomes, and in n chances. You see, when we perform an experiment, we may get the x, the desired outcome, let's say the head. It might be the first one. We toss the coin, we get a head straight away. We might have to toss it, if we're going to toss it 10 times, we might toss it again and again get a tail. But we might toss it a third time and get a head. So what we have to do is look at all the possible outcomes for where the head comes. So we'd have to record all the possible outcomes, and this formula simply does it for us. We can apply this formula NCX, and it'll give us the number of possible outcomes where the heads appeared. Perhaps, as I said earlier, we toss it 10 times and we don't get any heads. That's a possible outcome. Or we could toss it 10 times and get 10 heads. That's a possible outcome. what we'd expect to happen is we get 5. We toss it 10 times. We get 5 outcomes. So that particular NCX will give us the number of possibilities, the number of possible outcomes. And Px is the probability of getting x, getting ahead, which is 0.5, and 1 minus p to the power of n minus x. Well, that's the probability of not getting ahead. It could be written out alternatively in factorial notation like that, which I don't really want to get into because it's already done once, so let's leave it at that. But you may encounter it like that, and you should recognize it as the binomial probability expression. Now, suppose a dice is tossed 5 times. What's the probability of getting exactly 2 4s? Well, the solution is a binomial experiment in which the number of trials is equal to 5, the number of successes is equal to 2, and the probability of success on a single trial is 1/6. It's a dice. A dice has 6 sides. All dice have 6 sides. So the one that's shown on top, that has 1/6 of a chance of being there, because one of the other faces could have come up. So the probability of getting a particular outcome on one throw of a dice, the probability of getting a 2, if we throw a dice, and what's the probability of getting a 2? Well, it's 0.167 approximately, or 1/6, 1 in 6. There are 6 faces and 1 came up. What's the probability of that? Is well, 16.7% or 16.66%. Therefore, the binomial probability is, well, it's getting 2 4s, so the binomial is b bracket 2 4s. 5 times is the number of times we're going to try this particular experiment, and the probability of getting a 4 is 0.167. If we apply our formula, the one we had on the previous slide, and work it out, we get 0.161, 16.1%. So the probability of getting exactly 2 4s is 16.1%. In other words, the probability is that you will not get 2 4s. The balance of the probability would suggest that other numbers will appear. But sometimes we might want to work out the probability of getting exactly some outcome, so it's 16.1%. You can do that for no 4s, you can do it for 1 4, for 2 4s, for 3 4s, and so on. And if you add it all up, of course it'll come to 1, because one of these outcomes must appear. It may be that no 4s appear, or it could be 1 4, or it could be that 2 4s, because it's thrown 5 times. Only here I've calculated, I think, for yeah, 5 times, but here there's no 4s is a possibility, so there are 6 possible outcomes. Now, a cumulative binomial probability refers to the probability of getting a binomial random variable falls within a specified range. For example, it's greater than or equal to a stated lower limit and less than perhaps or equal to a stated upper limit. So it's in a range. They want to find the probability that's within a certain range, not just one answer, just one particular outcome, but a range of outcomes. Somewhere it falls within a certain range. We want to work out that sort of probability. For example, we might be interested in the cumulative binomial probability of obtaining 45 or fewer heads in 100 tosses of a coin. So we want to see what's the probability of getting 45 heads, or 44, or 43, 42. What's the possibility of getting any number, no heads even, all the way up to and including 45? What's the probability of that happening? This will be the sum of these individual binomial probabilities. So we'd have to take all the possibilities. The possibility of there being no heads, 100 tosses, 0.5 probability, and that's our first expression on there, plus b, x equals 1, so there's one head, again 100 experiments, 100 trials, again the probability remains the same, not 0.5, plus, and now it would be b bracket x equals 2, which is not written here, b x equals 2, again 100 trials, probability is the same, 0.5, so we'd have probability of x equals 0, x equals 1, one head, 2 heads, 3 heads, 4 heads, all the way up to, we've got here bx, x equals 45, again 100 tosses, and the probability is 0.5. So we'd have to work it out for each one. A cumulative binomial probability refers to the probability that a binomial random variable falls within the range, as I said. Now, there is a way of working this one out. Instead of just working each one separately, we could do it with Excel. The solution to solve the problem, we compute 46 individual probabilities using the binomial formula. The sum of these probabilities is the answer we seek, and as I said, that's the way we would work it out, and add it up so it becomes 0.184. So the probability of getting something in that range is 0.184. We could use the binomial distribution in Excel, which is an interesting way of getting. A coin is tossed 100 times. What's the probability of getting exactly 45 heads? Exactly 45 heads would be 0.184. So that would be exactly 45. The sum above it, actually they should add up to more than 0.184, because we should add up x equals 0, x equals 1, x equals 2, x equals 3, and so on, up to x equals 45. If it's false, then the probability of getting exactly 10 fours would be that sort of figure. So we can use the binomial formula to give different figures. So what's the probability of a student is accepted at a prestigious college? Let's say it's 0.3. If 5 students from the same school apply, what's the probability that at most 2 are accepted? To solve the problem, we compute 3 individual probabilities using the binomial formula. The sum of all these probabilities is the answer we seek. So the probability of no boys getting in, x equals 0, probability of 1 boy getting in, or 2. So what we've got then is that string of binomial expressions. B, x is less than or equal to 2. We have the 5 probability of is 0.3, I should say, the probability of getting in. 5 students. What's the probability that at most 2 are accepted? At most 2 are accepted. So we're ruling out the possibility of more than 2 being accepted. 3, 4, 5. So they can't happen. So we have the binomial of x equals 0. Nobody gets in. X equals 1. One boy gets in. So one student gets in. Could be a girl, I suppose. Doesn't say if it's what the gender is. And x equals 2. And then if we write that underneath, we find the probability of at most 2 are accepted is 0.83. Using Excel, we could use the binomial distribution and type in that expression and it'll give you the same answer. So it's a somewhat complicated video because of the terminology and because of the expressions and because of the way the formula are met and the way they crop up and we have to deal with them. What we need to know in this video is the conditions for binomial distributions. What are the factors we need to take into account? The probability remains the same, for example, that they are independent trials. And just look at the conditions that are necessary for the distribution to be used. And then how it's calculated, and the notation is complex. You need to become familiar with the notation, but this happens through use and exposure to the notation. So it's probably best to go back over the video several times and just become familiar with the notation and become happy with the way it's written. If you go online and look it up, you will also see the same type of notation is used online. So it's standard notation. What we need to know is the importance of the binomial probability distribution and the conditions that must be met before it can be used. But that's all we're going to deal with in this video, so let's leave it at that and say thank you for watching.